Good morning. We are team You've Got a Friend in ME, and the team members are Johnson, Dhruv, Anshul, Deep, and me, Karthik. And we are here to present on our topic vibration minimization across dynamic links of magnetically levitated nano-precise scanning stage by ASML. In order to understand our presentation, it is essential to first understand what a lithography machine is. A lithography machine is basically an engraver. It prints out lines in chips made from semiconductors, and those chips are used in basically everything like phones, laptops, and every single electronic device we use in our daily life. Graphy machine uses superheated plasma in order to generate UV light, which then fall on the semiconductor chips, and the material reacts accordingly, and this forms a desired patterns which performs various functions. ASML's top-of-the-line lithography machine currently prints at a scale of 3 to 5 nanometers. However, they wish to further push the boundaries of Moore's law and lower the resolution even more. One of the main things holding them back is the vibration present in the machine due to the cooling system and those generated by the cavitation of the reticule. Depicted in this diagram, the vibration across the long stroke travels through the dynamic link which is transmitting the coolant through it, and it disrupts the short stroke which increases the vibrations inside the machine and thereby reducing its accuracy. And right now we have developed solutions in order to reduce the vibration being transmitted. We have decided to go ahead with tuning and isolation to reduce vibrations, as we could not add mass because it results in expensive motor control requirements, and dampening was not applicable as well, as we are working well above the natural frequency range. Thus, we decided to go ahead with isolation and tuning. Is our function tree. In order to keep our mind open to fresh ideas, we have only concentrated on the most important parts that our project must cover, which was to detect vibration, calculate the adjustment, and transmit it, and at the same time reduce the turbulence in fluid flow and redesign the tube for lower vibration transmissibility. We have come up with a variety of solutions based on our function tree in order to reduce vibrations inside ASML's machine. To detect vibration, we are using an accelerometer. To calculate the adjustment, we are using a microcontroller, and to transmit the adjustment, we are using an actuator. In order to reduce the vibrations caused by the cooling system, there were a number of factors that needed to be considered, such as lowering the fluid velocity, introducing an air pocket filter, redesigning the tube itself. However, we have combined all of this in order to create a passive isolating model which reduces the turbulence caused by the coolant system and also absorbs the vibrations caused by the long stroke of the carrier.
The passive isolation module aims to isolate rotational and translational movement from the system while maintaining constant coolant flow and preventing leakage. The CAD model shown is a section view of the module, and the red arrow indicates the direction of coolant flow. The module achieves isolation by using discrete angular and linear couplers, which isolate rotational and translational movement respectively. Each independent module provides 4 degrees of freedom. The angular coupler provides 3 degrees of rotational freedom, and the linear coupler provides 1 degree of translational freedom. The module attaches to both the clamp and the carrier, which are perpendicular to each other. This means that the system as a whole has an additional translational degree of freedom, which means that the system has 5 degrees of freedom in total. Please note that the grooves shown, known as glands, are for seating the O-ring seals to ensure water tightness, which will be discussed in detail in the upcoming slides. The angular coupler acts like a ball and socket joint. Coolant enters from the ball, the male part, into the socket, the female part. The coupler restricts pitch and yaw movement to 32 degrees to ensure coolant flow and a tight seal, but permits full 360 degrees of roll motion. Note in figure 8 that the bottom of the female part is threaded, which allows us to attach the linear coupler to the angular coupler. The linear coupler behaves like a piston and cylinder. Coolant enters from the piston, the male part, into the cylinder, the female part. Note that the piston attaches to the bottom of the female angular coupler. It provides freedom of heave movement, that is up and down movement, in the clamp, and sway movement, that is side to side movement, in the carrier. The motion of the coupler is restricted to 5 centimeters of displacement. O-ring seals were used to ensure that the module is watertight. Most seals are static, but ours is dynamic because we have relative motion between sealing surfaces. This adds some complexity to the choice of O-ring used because we need to ensure a tight seal while also allowing for unrestricted motion. We also need to account for wear and tear caused by friction and oscillations. Keeping this in mind, we decided to use 5% compression on the sealing surfaces to overcome resistance due to friction and stretch the O-ring 2% to ensure a tight seal between the O-ring and the gland. While resistance due to friction is low, there may be insufficient slip between the sealing surfaces for small displacements, in which case the O-rings would experience shear deformation, which would provide isolation. Figure 17 shows a cross-section of the linear coupler, which demonstrates how the O-rings were used to ensure a tight seal, and figure 18 shows an exploded view of the module, which demonstrates how it was assembled.
Active cancellation system, we have decided to go with an Arduino-based linear actuator system, which uses an accelerometer to detect the vibrations, and then it moves the linear voice coil actuator accordingly in order to cancel out the vibrations generated by it. We are using a PID controller to do this. Is the block diagram for our PID controller. So the sensor detects the vibrations being generated and it sends it in a loop to the controller, which further outputs it into the linear voice coil actuator. And this loop keeps on going on in order to cancel out the vibrations continuously. This is our experimental setup that we have used to collect the data in order to understand the efficacy of our system. The baseline model is on the left along with the active tuning model and the isolation model so that we can compare the performance of all three of them and come up with a viable conclusion. We will be presenting this further in the expo and we look forward to seeing you there. Thank you so much for your time and we hope you have a good day.